Okay, so continuing, um, looking at looking at the HR diagram. Oops, oh, not here. Looking at the HR diagram, there you go. Look at the HR diagram. So you can find hot stars, either big or small, on the left-hand side. So hot stars are found on the left-hand side. So the first row you should mark left. So going over here, so you should mark this one left. How about faint stars? Faint stars. So you go in the HR diagram. Faint stars are those that are not luminous, right? So they are pretty much in the bottom. Could be bottom left or bottom right, but they are faint. They don't produce lots of energy, basically. So that should be bottom part. How about luminous? Luminous are those that are strong, put a lot of energy, so they are pretty much on the top part. They can be luminous cold or luminous hot, one another, right? So it doesn't matter. And so it's pretty much top. How about cool stars? So cool stars um, are found where? Here. They can be cool luminous stars or cool subluminous or faint stars, right? So they are pretty much on the right hand side, right there. Now, the other exercise is check the appropriate region of the HR diagram corresponding to each description below. Large blue stars are found where? So go back there. Large blue stars. So large, you are talking about the top part. And blue, here they are. Right? See how big they are? And then you can also look at the iso radius lines. See these lines over here, the green lines? So these green lines indicate stars that are 100 times as big as the sun. This symbol here, R, and a circle with a dot in the center, is the solar radius. The radius is, for instance, let me draw here. So you have a circle. This is the radius of the circle. So this symbol is the symbol of the sun. So the solar radius, stars with 100 times solar radius, they are somewhere here. They can be cold or they can be hot. Okay. But we want to find the large blue stars are found where? On the upper left, right? So then we would mark right here. And small red stars. So small, you're going to go to smaller radius. So red means somewhere here. So we are talking about what? Lower or bottom right hand side. Bottom, what is it? Lower right hand side, right there. And then the small blue stars would be lower left hand side. And really large red stars are on the upper right. And they are red because they are cold. So the equation below describes the luminosity. That's the basic equation that relates the amount of energy the stars are sending, right, to their size. And here you have their size square and their temperature to the fourth power. And luminosity is energy, basically. So think about luminosity of a star, the number of 100 watts light bulb you wouldn't need to go to Home Depot and buy to yield the same amount of energy that particular star is sending out. So basically, the luminosity depends on how big the star is and also how hot the star is. But as I described in class, the size of the star is more important because the size of the star, the temperature of a star, the range in which the temperature of stars change is a range that goes, let's say, from 3000 Kelvin to 30,000 Kelvin. And I don't want to put a lot of a math on your brain, although math is good. If we are good in math, we don't need to pay somebody to think and make a decision for us. But the range in which temperature changes is a factor of 10 from the coolest member to the hottest member. Now, the range in which the radius change, if you look in the HR diagram, the range in which the radius change, especially in the main sequence, is one that is 1/10 of solar radius to 10 times, or in the case of supergiants, 100 times as big. So you have a range that goes from 0.1 to 100 times, right? So although the radius here go to the square, right, to the power of a square, temperature goes to the power of 4. So if you think about power, temperature seems to be more relevant here. But the radius of a star is something phenomenal. It's not a small number like temperature is. It's a big number. And what determines the luminosity is the size of the star, right? Although go to the square. So the size of the star, the bigger the star is, the more luminous the star will be. That's why the sun now has the size that is matching 100 times the size of our planet Earth. But when the sun becomes a giant, as you can see in this HR diagram, if I bring the luminosity classes, when the sun becomes a giant here, the sun is going to come out of this position, right? And it's going to rise up to be a red giant. So the sun's radius go 10 times as big. It can be 100 times as big when it goes to the asymptotic giant branch star. So 100 times as big means the sun is going to be heck of a luminous, and although, as you can see in this diagram, its temperature will not change that much. So the size changes significantly, but not the temperature, and therefore the sun becomes more luminous, as we can inspect in this diagram. So for us, Astro 10, what do we need to know? Well, we need to know that the luminosity, the energy the star itself sends out, depends primarily on its size. Big stars are luminous. Please, this is going to be in your final exam. Now let's look at the main sequence. Here's the main sequence. In the green locale is where the main sequence are. And the main sequence stars are stars that are undergoing fusion reactions of hydrogen and helium, like our sun. And these fusion reactions produce new elements, helium for instance, but also produce the energy that keeps the star stable. So the star in the main sequence changes slightly its size or its luminosity, but not significantly, because there is a steady production of energy in its central core, and that steady production of energy keeps everything stable. Okay. Now, what we studied previously, the luminosity varies with the mass with this funny factor that luminosity is the mass is proportional to the mass to the 3.5. So, which means is that when we look at the HR diagram, submassive stars are here. Stars that have a mass that's subsolar, as we say. So the mass is 10th of the solar mass or half of solar mass. And in stars that are more massive, they happen to be in this position in the HR diagram. You might be studying in your lecture course, that stars, there are less than 8 solar masses, 8 times the mass of the sun. They are considered low mass stars. In stars that are more than 8 solar mass, they are considered high mass stars. And their evolutionary pathways will be different, right? Low mass stars will end their lifetime as planetary nebula and white dwarfs, whereas high mass stars will end their evolutionary sequence as a neutron star or black hole. And in between their main sequence phase and the corpse we call black hole or neutron star, there is a phenomenon called supernova. So they explode and they produce all these heavy atoms we are used to see. Now, to construct a conceptual HR diagram, there you go. So you should be able, for instance, in the final exam, having a written part, I could ask you to complete the HR diagram. So then you have to be able to write what it is. So you have a temperature down here, and you have a luminosity right there. So you put tick marks beginning with, you put tick marks beginning with 0.1, and then you put another one that is equivalent to the sun, and then another one that's 10 times as big as the sun, another one that is 100 times as big, and that is pretty much mimicking what we got right here. This is 100 times, and then 1,000 times, 10,000 times, 100,000 times. So you can just keep on going. 10,000. No, this is 1,000. 10,000. So go 1, 2, 3, 4 zeros. And then the last one is 100,000 times. Okay. 2, 3. And down here for temperature, you could start with 50,000, but here's 40,000. Just to remember, I like to start with 50,000. Doesn't matter. Just conceptual. 50, I go to 10. 10,000 Kelvin. And then 5,000. And then the last one, 3,000. Got it? Now, what is the sun? The sun is a little bit hotter than 5,000. It's 6,000. So the sun is somewhere here. That's the sun. 1 solar luminosity and about 6,000 Kelvin. And the main sequence is somewhere here. Then you draw the main sequence. Right? You draw the main sequence. And then you call, looks like a Santa Cruz slug. Main sequence. And then you have the giant sequence right here. We have the super duper giant right there. Super duper giant. And down here we have the white dwarfs. That's it, right? That's it. Then you know what's going on. Um, you simply want to draw arrows showing the direction in which variables are increased. Draw in an arrow on the y-axis showing the direction of increasing intrinsic luminosity. So we did more than that. So if you can reproduce that, you were good. But basically, in the main sequence stars, you have 90%. See, if you shoot stars in the sky, if you happen to take the region where 90%, no, the region up, let's say, 30 light years away from us, right? So imagine we could visit all the stars within 30 light years, closer to us. And if we manage to do that, the majority of the stars, 90% of them would be main sequence, right? And in fact, next week, we are going to build an HR diagram of the closest stars. Uh, and what we would learn is that the closest stars happen to be sub-solar mass stars. They are not big. They are, in general, very small. And they take long time to complete their evolution. And the stars that are the brightest star in the sky, they happen to be supergiants. They are supergiant stars. Okay. So next class we are going to explore more of these aspects. Now the end of this handout is to certainly explore the instability stripe. See this red region over here? In this region, some stars, they undergo pulsation. And this pulsation means their luminosity change periodically with time. And they are important, very important. They are key stars in our courses, both lecture and lab, because these stars enable astronomers to establish the first ruler enabling them to measure distances in our galaxy. And the reason to that was these variable stars, their variation in luminosity is tightly correlated to their distances or to their luminosity. It's called it is called so basically if you can observe, let me see if I can write in here. Yeah, I can do here. So let's say you observe a star, and you don't need to have an excellent observatory, but you observe a star and you note their brightness change over time like this. And then you can say, okay, if I had enough observing time, I would see the variability to go like this, right? And so this is pretty much brightness, and this is pretty much time. Time, not temperature, but time. Okay. So if you measure this time, so this is a time, between equal part of the curve, which means the time that it takes the star to go from its brightest point to its brightest point again. If this time is less than 1 day, the star is called RR Lyra. RR Lyra. RR Lyra. Lyra. And if the variability is more than 2 days, these stars are called Cepheids. Cepheids. Oh, I can use this Cepheids. Okay, this is 2 days. 2 days, 1 day. So what does this tell us? Well, it tells the following. If we can identify the period of the star, astronomers were able to prove that the period, which means the time it takes the stars to go from peak to peak, is correlated to their luminosity. In other words, if you observe the star and just get the time they take to go from peak to peak, you can get a pretty bright measure of their luminosity. And why is this important? It's important because, as we saw previously, the luminosity of a star divided by 4 pi times the distance to the star square is equal to the brightness. Brightness is what we observe. Luminosity is the energy the star itself is sending out. And again, if you just measure the period of the stars, you have the luminosity. So these luminosities measure as a result of this scale. The brightness, you just observe the star. What you got? You got the distance. So our galaxy was mapped by astronomers in the early 1900s, so its size and its dimensions were all mapped. And in fact, the distance to nearby galaxies was initiated when these pulsating stars ended up being found. And in fact, a Cepheid was found in Andromeda galaxy, and that was the first time astronomers were able to establish a distance to Andromeda as 2.5 million light years away. Okay. So in other words, what this instability stripe is important for? Well, is a stripe, is a region in the HR diagram if the stars have the proper mass, which means they are somewhere here. When they evolve off the main sequence, they're going to go through this pulsating phase. And as they go through the pulsating phase, you can have a strong grip on their luminosity. And having a strong grip on their luminosity enabled astronomers in the early 1900s to have a grip on their distances, and then a whole scale to our universe was established. Okay. So next week, lab, as I said, you are going to build an HR diagram and an HR diagram of close stars and faraway stars and bright stars, in fact. And we are going to use Stellarium for that purposes. If not, perhaps the Starry Night software, one of them. And so that's it, folks. Make sure you complete your assignment. Again, this stellar evolution is an important component of your final exam, as the moon was important in your midterm. So I'm telling you, there will be lots of questions with respect to stellar evolution. And if you are not there yet, talk to me and then we can work something out. All right? Okay, that's it. Did you get any virus? Nah.